Welcome everyone to the 8th seminar of the On Things to Come webinar series of the International Space Science Institute, Beijing. Our On Things to Come seminar series was started last year in September, and it's dedicated to ongoing and future space missions. So we invite outstanding international scientists to present space missions from different space agencies. I am Laura. I am the PR manager of ISSI-BJ. We have here Professor GAN, our guest speaker today. Thank you very much for accepting our invitation. And you can see in the webcam also Professor Ip, who is the executive director of ISSI-BJ. Before I introduce very briefly ISSI-BJ to those who are not familiar with our institute, I would like to say a couple of words about this platform to make sure everyone can follow the seminar successfully. So ideally you should use Chrome or Firefox so that it's going to be more stable. Ideally you should also turn off your antivirus and close any other window, because the streaming platform needs a very, very stable connection. If you still have problems with the platform, with the streaming, you can take a look at the link I just sent in the chat box. Bilibili, it's a Chinese platform, so especially for those of you who are in China, the streaming is very smooth there, and you don't need to download any app. So briefly about ISSI-BJ, the International Space Science Institute Beijing was established in 2013 thanks to the collaboration between the International Space Science Institute in Switzerland, Bern, and the National Space Science Center of the Chinese Academy of Sciences. It's a research institute for advanced space science studies, as you may know, and we organize a wide array of events all over the year. We organize workshops, forums, international teams. We have working groups, and so on. Unfortunately, given the epidemic, we haven't organized any event in 2020. We will see if it's possible to have face-to-face meetings this year. But in the meanwhile, we have started this On Things to Come webinar series, and also another webinar series started last Monday in Chinese, called Tianfan Yetan. So if you want to follow that one and you speak Chinese, you're naturally welcome. So without further ado, I would like to give the floor to Professor Ip, and thank you very much for being here.
Yeah, thank you, Lola. And we want to thank Professor GAN for accepting our invitation to give this talk on the ASO-S mission. But let me first, introduce Professor GAN, say a few words. Professor GAN is currently the chief scientist of the mission, the Advanced Space-based Solar Observatory, initials ASO-S mission of the Chinese Academy of Sciences. And Professor GAN, he did his PhD at Nanjing University, and he received a PhD degree in 1989. Then he worked at the Purple Mountain Observatory and became the full professor in 1995. And his research specialty is on X-ray and gamma ray observation of the sun. I remember the first time I met the Professor GAN must be in the middle 90s, when he and his colleagues from Purple Mountain Observatory and the National Astronomical Observatories in Beijing came to the Max Planck Institute in Lindau to talk about the possible cooperation on a Chinese solar telescope missions. So I'm extremely happy to see that, Professor GAN now is talking about this first Chinese solar mission. Professor GAN, please.
Okay, thank you, Professor Ip. Thank you, Lola, and thanks for ISSI-BJ for providing me this excellent chance to introduce you our mission, ASO-S. So before my talk, I would like to explain a little this then ASO-S. So about 10 years ago, we Chinese solar physics community to discuss the future 10 years or 20 years later, then we made some strategical studies for the future. At that time, we proposed we would like to establish Advanced Solar Observatory, both on ground and in space. Then we have learned ASO-S, space-based. So in principle, it is a general, not a specific name. But when we have these missions, then when I realized that it is a general, not a specific lens, I found it's very difficult to change it because in a lot of documents, we have already written down this then as a specific lens. So don't think it so seriously, but just it's a lens. So, and here is my talk of the outlines today. So I would like to introduce a little the background. Then I focus my contents mainly on the scientific objectives and especially on the payloads and the latest progress of the payloads. Then I mention a little the mission profiles and platform. Finally, I introduce you some perspective for the future, scientific return, especially how to organize the scientific research. So yeah, the first picture, then second picture. Yeah, the third one. Okay, so maybe you know before we have no solar dedicated missions before in China. So ASO-S should be the first Chinese solar missions. When we proposed these missions, we have considered a lot of questions. For example, certainly the mission should deal with the frontiers of the research. The mission should be different in some way from the existing ones. Another important issue is that we hope the first mission should be involved by more peoples, not only interested by only one group of peoples. So, and then we should have good background, both in researches and in techniques, especially for the payload technologies. And we also like to make use of the opportunity of 25 solar maximum. Otherwise, as you know, if we focus on the solar activity, we have to delay a lot, 11 years. When we consider all of these issues, maybe our ASO-S is the unique. Here is the statistics for all the papers, reference papers published in 2015. Total number, you see, United States takes about 26%. Then China takes 12%. So from here, you see China published 12% papers, ranking the second just after United States. But I would like to remind of you, the data used in these papers are mostly from the space observations. But it does not mean we have done nothing. As a matter of fact, before the ASO-S, the Chinese solar physics community have made great efforts. The first Chinese astronomical satellite was proposed 45 years ago. Then in 1990s, last century, Professor A proposed Space Solar Telescope. Then in the beginning of this century, maybe you have known the Prof mission, then a SMAS mission. SMAS mission is a joint China-French solar physics, smaller explorer for solar eruptions. That is a joint French and Chinese missions. But all of these efforts has not been gone to the final launch stages. Anyway, so these previous efforts provide the basis for our ASO-S missions. One of the successful space solar observations by Chinese astronomical societies was made in 2001. That is on the Shenzhou 2 manned spacecraft. There are 3 payloads. One is we call super soft X-ray detectors, gamma ray detectors, and X-ray detectors. Here I show you some examples of the observations. For example, the gamma ray detectors observations in comparison with the Yoku WBS you see. And here is the X-ray detector observations in comparison with COLOS observations. So for the history of the ASO-S, in 2011, the conception study was proposed. Then we underwent intensive extended studies. In the end of 2016, the official phase 0 and phase A was got the support by the CIS. The most important date for our mission is the end of 2017. At that time, our mission was got officially approved. Then we start our phase B studies. Now we are at here. The phase C studies will be finished by this month. Then we will start our phase D studies. We expect the phase B study will continue for about 1 year. Yeah, by the end of this year. So as you know, there are 2 most well-known phenomenon on the sun or in our solar system. One we call the solar flare. It's a local eruptive phenomenon. Another one is we call coronal mass ejection. It is a global eruptions. Both of eruptions are the most well-known phenomena on the sun. If we see more closely, so here you see the magnetic field evolution, then we may expect solar occurrence of the solar flares. So, but as you know, at the moment, the time resolution is not very high. So the quantitative relationship is we still need to be studied. Nowadays, we believe that the energy of the solar flares and coronal mass ejections are now originate from the solar magnetic flare. So the observations of the solar magnetic field, solar flares, and the CME, we prefer refer it as 1N, 2B. 1N, the magnetic field, 2B means 2 bursts, flares, and CMEs. To observe 1N, 2B simultaneous on a single platform, and the researches on the relationship among them are particularly important. So there are 3 key questions for our missions. One is the relationship between the solar flares and the magnetic field, the relationships between the CME and the magnetic field, and the relationship between the flares and the CME. How does the solar magnetic field can result in the occurrence of solar flares and occurrence of CMEs and both flares CMEs? That is, we should want to study it. So extendedly, we can list a quite number of questions. For example, for the relationship between the flares and magnetic field. For example, what is the role of magnetic shear and the emitters in storing and triggering solar flares? What is the relationship between the magnetic topology and the reconnection region which result in solar flares? What is the rare magnetic change before and after the flare? What is the rare magnetic energy empowering the solar flare? What factor controlling the energy portions among thermal, non-thermal, kinetical, and wave, and so on? What are the diversities for partner situations? So similarly, for the relationship between the CME and magnetic fields, what is the precursor of CME, especially in the relationship to the initial states of solar magnetic field. What is the quantitative relationship between the magnetic complexity and the production of CMEs? What is the role of magnetic groups in the formation of the CME? Yeah, it's a very hot topic today. And is the CME triggered locally or globally? Is larger scale connection existed in the CMEs? What is the real role of larger scale magnetic connectivity in CMEs? And can we use helicity to predict CME and so on? So for the relationship between the flares and the CMEs, so is there a causal relationship between the flares and the CMEs? And what is the factor containing strong, weak, and long-range connections between them? What is the physics of small-scale changes resulting in larger-scale disaster consequences? How does the magnetic energy distribute among the solar flares and CMEs? Is the flare without CME differ from that with CME or vice versa? What is the difference of flare accelerated particles from that accelerated CME and so on? A lot of questions. When we consider all of these issues, we proposed 4 scientific objectives for our ASO-S missions. The first one is we would like to simultaneously observe the long-thermal images of hard X-rays and formation of CMEs, so that in order to understand the relationship between flares and the CMEs. The second, we would like to simultaneously observe the 4-disk vector magnetic field, the energy release of solar flares, and the initiation of the CMEs in order to understand causality among them. So the third, we would like to observe the responses of solar atmospheres to the solar eruptions to understand the mechanism of energy release and transportation, as well as the patterns of the dynamics. Certainly, in this we need to combine the other ground-based and ground and space-based observations together, so that we can study the different layers, get different layers of observation, we combine them together. The fourth scientific objective is we would like to do something in the space weather. That is, we would like to observe solar eruptions and evaluations of solar magnetic fields to provide clues for forecasting space weather. Especially, we would like to observe the inner corona, how the coronal mass ejection proportion in this area. Then we would like to make a real-time prediction for the influence of the CME on the Earth. So, in order to fulfill with the scientific objectives for ASO-S missions, we proposed 3 payloads. One we called the 4-disk vector magnetograph, that's FMG, to observe the 4-disk vector magnetic field. Here. The second payload we called hard X-ray imaging. Here, to observe the long thermal spectral imaging of the solar flares. The third instrument we called LST, Llama Alpha Solar Telescope. There are in fact 3 telescopes, coronagraphs, and 2 disk imagers. So both these 3 instruments corresponding to the 1N, 2B, as I mentioned before. 1N, that is the FMG to measure the magnetic field. First one, solar flare, was observed by the hard X-ray imaging and the coronal mass ejection by the LST. So in principle. So if we compared our payload arrangement with the other missions, for example, Stereo, Hilodi, SDO, Park Solar Probe, Solar Orbit. So you see, for example, for the SDO, so there's no coronagraphs, there's no hard X-ray images, and so only here, from here you see only the solar orbit, we have a similar arrangement of payloads, but we can make a joint studies. For example, for the hard X-rays, we can observe from different different point. We can make a stereo observations. Then we can study the anisotropic of the hard X-ray emissions. So it will be the first time for the X-ray image from different angle of the observations. So anyway, the characteristic of our mission is on a single platform to observe simultaneously the 1 and 2Bs. That is the characteristic of our mission. So the first instrument, as I mentioned, is the FNG. FNG, here's the optical design. The PI, the chief pilot scientist is done from Beijing, and the chief engineer is done from Nanjing. So here's the optical design of the instrument. Key part is the polarization analyzer here, then filter system here. Another key part is the filter system here. Here is the mechanical design. And the mission is to observe the 4-disk vector magnetic field with a relatively high temporal resolution. Here is the parameters of the instrument, the field of view for the 4 solar disk, and apertures, and here's the resolution and detector and so on. Here's the working spectral line is at this line. This line is also be used in the while observing stations. Here's the 4 ways, half maximum, and here the sensitivity for the longitude magnetic field is about we proposed a 5 Gauss. There are some key technologies for this for FNG. The first one is the insurance window. So a reference to the SDO and other instruments. So we proposed the so-called sandwich structures. Here is the filter properties. You see, after sunlight goes through these windows, only this waveband can pass through. The other waveband can be excluded very rare. So you see here, and the key technology is the so-called image stability systems, because we need the stability is about 0.25 arcsecond per second. So we mentioned the length of the sun and the feedback, the singular to here to control this mirror. Here is the prototype model in the laboratories. So after now we can get this data proposed. And another key part of this instrument is the filter. So we use the 7 units of the filter systems. So after 7 filters, we can get a very narrow line. This line very narrow. So here is the prototype of the model. So the total transmission should be bigger than 8%. So now the whole instrument has been finished and has delivered to the satellite. So here's the instrument. Was doing some environment experiments like vacuum, vibration. The most important progress is we use this instrument in while observing station to do some test. Here's the test results. So you see the FNG original data. After some treatment, after calibrations, you see the magnetic field. Here's the results by the SDO HMI. So you see very similar. So the test observations show the instrument satisfying all the requirements designed. The longitude longitude sensitivities can reach to 2 Gauss, much better than what we proposed. The second instrument is the Llama Alpha Solar Telescope. Dr. Chen from Changchun is the chief engineer, and Dr. Li is from Nanjing is the payload scientist. Here is the outlook of the instrument. There are 2 layers. The first layer here is the optical design, is the we call it Coronagraphs working in the Llama Alpha. So mirror 1 and mirror 2. After mirror 2, it got only the corona night. So then there are 2. One night is for the Llama Alpha, and that is for one night. In the second layer, there are 2 telescopes. One working on the Llama Alpha, another working on the one night. So the instrument is to observe the Llama Alpha and one night of solar images up to from center to up to the 2.2 solar radius. Here's the parameters of the LST, coronagraphs. Here's the diameters, and so you see coronagraphs as well as disk images working on these 2, working on Llama Alpha 9 as well as the one night. So you see there are some overlap for the field of view, so that we can follow better the origin of the CME as well as the proportions close to the sun. So also you see, as you know, the most important issues for the coronagraph is the string night. How to suppress the string night. So the first factor we should consider is the N1. So we should manufacture the super polished N1. So RMS roughness should be less than 0.2 millimeters. Here's the mirror we have manufactured. The second one we should consider is behind the N2, we designed a lot chips here. There's lot chips, then to suppress the straight night. A large factor we considered, we arranged a Leon stop A1 at here, and to remove the diffracted ring formed by this A0. Besides, we also simulate the mechanical structures. The straight night from the mechanical structures does a lot of simulation on how to improve how to suppress the straight night. We did some simulations, and we also developed some facilities to measure how to measure this straight night in the laboratory in Changchun. Here's at moment, maybe 2 months ago, here's the experimental results. For these 700 millimeters, they can get 2.10 to 10 to minus 7. Yeah, it is almost, but it's not as good as we proposed, but it's very close to. Now the whole instrument of LST has been ready in the laboratory, and finished all the experiments like web operation and Weiqun and so on, and has delivered to the satellite platform. All the tests for the engineering model has been done, and the performance presented are satisfying the requirements designed. The analysis on straight line are still undertaking stage. The third instrument, the hard X-ray images. The Zhang from Nanjing is the chief engineer, and Yang Shu and Jian Wu is the payload scientist. For this instrument, so there consists of 3 parts. One we call collimators, including the front grids, rear grids, and these structures. And here is the detector, we call the spectrometer. Then there's the electronics control. So here you see there are, we call it aspect systems. There are two cameras here. So one is mentioned the center of the sun. The other is to observe the deform of the whole structures. Both parameters are important when we treat the data later to do a reconstruction of the images. So this instrument is to use to observe the long thermal spectral images. Here is the parameters of the instrument. So it's energy, range, so up to here, and energy resolution, spatial resolution. For the grants, we totally we have 91 grants, but we have 99 detectors. So here is 9. Here is 9 times 11. But due to we arranged some grants to mention the background as well as the total flux. So the grants only 91. So here's the other parameters. So here's the total distributions on the grant platform on the pledge. So totally we have 10 groups with different pitches. For each pitches, we have different orientations. Here's the distribution, the optimized distributions on the grant pledge. So from the French grade to the back, they are about 1.2 meters wide way. And each area of the single grant is about 2 centimeters square. Here's the detector. We use LABR3. Now, the key technology for us first is about how to manufacture these grants, because the material is very hard. So we use a laser machine to manufacture in a very thin layer to get a grain. Then we stack up to the thickness what we require. Here we develop some different methods, techniques, how to stacker with high precision. Here is I show you example with the finest 36 macro and the thickness. So it's different grains we have made. And the key technology is about how to make a line of the collimators, because as you know, the range is very narrow and there are 1.2 meters 5 ways. How to make alignment is very key. So in a words, we put them together at first, they can go to alignment, then we take it 5 way, then we mention the reference, we take some reference, we mention the reference, then we assume the alignment of grains from front to the rear can ensure this the alignment. So there are a lot of techniques I don't mention here in detail. And the other key issues is about the structure of the collimators. So after a lot of simulations and tests, we propose that the temperature between the front and the rear should be less than 1 degree. Otherwise, so it's hard to get the realized the imaging reconstructions. So, and now the instrument has been finished, and here is the 3-part detector and electronics box. Here's the collimators. We combine them together. Here is the here we did experiments for the beam. Here is the results of the beam test. So sine, cosine, and almost the same as we expected. at the moment, the phase C study of this instrument was successfully finished by the end of last October, and the integration tests with the platform are being undertaken, which will be finished soon. The home missions, the mission will work in the orbit. Here we call this solar synchrotron orbit with altitude 220 kilometers. This altitude of the orbit we consider both for the coronagraph as well as hard X-ray background. And here is the, for example, a stability of the mission. But as I mentioned, for the LST and for FMG, they have their own stability subsystems. So we plan to launch the satellite in early 2024. So this the platform will be manufactured by the Innovation Academy of Microsatellite in Shanghai. So here's the photo I took last month. So you see all the three instruments has been installed on the satellite. They are doing some tests, electric tests, environment tests, and so on. The phase C study of the whole mission will be finished before the end, just this month. Then the phase D study is scheduled to be finished within 1 year. So here is the latest picture of our missions. So for the science returns, here I show you our science application systems, which is responsible for the scientific research. And there are 4 subsystems. The first one is the scientific operation, then the data management, then user service, then the data analysis center. Now we finished the computer room, and for this month, finished the computer room as well as the operation rooms. So for the application systems, the most important, I think, is the data analysis center. So we arranged 3 data scientists who are responsible, respectively, these 3 instruments. So we also built our homepage of our missions. In the future, all the service, all the connections with the user will be provided in this website, especially for here, the data, software, and so on. But these websites are still in constructions. We also established the International Science Committee, committee. This special committee will provide advices on some important issues, like data policy, and so on. So you see here a lot of Hugh here, Hugh is here, so a lot of internet. Here's Jean-Claude VR here, and so a few months ago, we just finished the data policy of our missions. So in a few words, the scientific data are completely open. That is the principle of our policy, is completely open. That means all users have the same right to use the data of the ASO-S mission as the team members. Certainly, we encourage the collaboration between the team member, and so other details. We have already put this data policy on the website, so I don't mention. So for the FMG, so we plan to provide the data at different levels, and also we plan to provide the software to decode the data and the code to extract the magnetic neutron line, for example, get the comprehensive magnetic graphs. And we also plan to provide the code to extrapolate the local and global magnetic field, and the code to get some fundamental parameters, and so on. So, and for the LST, so here is the products of our instrument. So we provide these coronagraph images both in Llama alpha and in white light, and we also provide both the disk images in Llama alpha and in white light at the highest time resolutions. So beside these images, we also provide some software to extract the mass, temperature, velocity of the CME, and also we provide the parameters, the code, the software to extract the parameters of prominence, flares, and so on. So we also will provide the flare list and also the semi-list based on our mission observations. For the hardware surveys, we plan to provide the six tools to get the imaging reconstructions. We call the basic algorithms. Here's BP, back projection, and clean and forward fetch. That's based on that is pattern based, and then we provide the visibility based for the with BP and with clean and with forward. But we still plan to provide other algorithms, but at the moment we don't promise we can do, but we will try. Certainly some need to do some international cooperations. Here we finished to simulate the larger flare or a middle flare, and we consider not only the instrument but also of the background, the orbit background. Then when we have this data, then we can try our method. Here I show you examples. Just the input source there. Then we use different methods so we can get the image reconstructions. Here is I show you an example, and the software interface. We try to provide a friendly interface, then the user can easily use it. So, and we also hold a series of assembly. Our plan is to hold once a year. So since the 1980s, we have the first domestic ASO-S assembly. Then in 2018, we hold the first ASO-S international workshop in Nanjing. So some people here you see very, yeah. And in last November, we hold at domestic meetings, ASO-S assembly, in Xiamen. So about 200 participants attend the meetings. So in this year, we plan to hold second international workshop of the Coronagraph. Maybe I'm not sure. Maybe we have to delay it to the next year. We also have some international cooperations with international colleagues. Like we have some collaboration with the Poland colleagues. So now we have published two special issues. One appeared in RAA. There are 14 papers describe the whole field of the mission. So if you want to look more details, you can read these special issues here, ASO-S special issues. If you want more details of the instrument, so you can also read, but here Chinese, but also we translate it into the English. So that's a special issue in Chinese. So both the special issues. And here is the website of our ASO-S missions here. but still in construction. We try to improve it. We start going to summarize my talk.
So,
yeah, moment. Okay, thank you very much. Thank you.
yeah, thank you so much, Professor Gan. So let's see whether we have questions from the audience.
We have the first one by Professor Michel Blanc. I think Professor Gan, you can read it. He thanks you for the very nice talk, and he would like to know more about collaborations with Solar Orbiter. Do you plan on periods of joint observations for global imaging or observations? Yeah.
Yes. At the moment, we have established connections with Solar Orbiter group. One is with the STIX team. Yeah, with STIX team, we have already got a support, a grant. We have got a grant to support, especially the collaboration between the STIX and the HXI. As I mentioned, so it is the first time we from different angle to observe hard X-ray imaging. So we believe we can get some very interesting results, like the directivity of accelerated particles, anisotropic or not. So a large collaboration is the Mertis team. So in our the team members of our LST, many people has joined the discussion with the Mertis. So I found the Mertis, the model of Mertis is very helpful to provide us a reference in the future, because they have formed different groups, a lot of groups, and to focus on different topics. I think it's very nice, very nice. So just last month, with science team, with ASO-S science team, we also have a meeting, and we try to learn something from this model of Mertis, and we also try to establish our own teams and to focus on some specific research topic. So yes, at the moment, yes, we have established the two connections. One is with the Mertis, one with the STIX. Maybe in the future we can establish more collaborations. Okay, thank you, Jan Crowder.
Thank you very much. Next question comes from Iman Scalia. Would it be possible to incorporate the measurement of magnetic fields directly in the corona into your coronagraph?
Yes, as you know, we mentioned the photospheric magnetic field. Yeah, magnetic fields. So we have to use the as a coach to extrapolate from the photosphere to the corona. Yes, this needs some time. So yeah, what we mentioned, we study the relationship between the corona, corona mass ejection and with the magnetic field. That means not for the real time. That means after we got the data, we study the relationship between them. If we make clear the conclusions, then in the next time when we observe the similar magnetic field, we can predict when the corona mass ejection will happen. So this is a later study, not the real. This relationship was not we do study at in a real time. That's afterwards. I'm not sure whether I get your question or not. Sorry.
Thank you. Next question from Professor Vial. What are your plans for photometric calibration and survey of degradation, especially for alpha?
Yes, we have discussed this for a long time. So there's a small group of people working on that. So in my understanding, they have already published a paper in Chinese. So they would like to use a style to do such calibration. The alert method, in my understanding, they also have a light. They arranged a light source. Then they can do calibration by themselves. So I'm not so sure. So anyway, so we have considered these calibrations. So absolute calibrations. So yes, we have done. Sure.
Perfect. Next question.
For Professor Hunter, we don't measure the magnetic field in CME using D3 lines. No. So
now, the next question is Ivan Zimovets.
For Ivan's questions, yes, we can observe the soft X-rays. In fact, below, around 20 kV in principle, yes. And for VR, at this moment, we didn't make the polarization measurement for the Llama alpha, but really we have some polarization measurement for the white light. So we cannot get the corona magnetic field at the moment. So here, because we have no anti-shared system of our HXI, so the background is relatively high. So we cannot expect we can measure the smaller flares. We expect we can measure only N-class flare, above N-class flare. So that is the problems of our instrument. And yeah, Birgit, what is the wavelength range of Llama alpha? So the wavelength is about 10 astron, about 10 astron. So the wave, yes.
Okay. Any other question that you want to answer? I think most of them have been answered. Eventually, since time is up, if you have any other question, feel free to submit it or to send me an email, and then we can forward it to Professor Ghani if he agrees. And also regarding someone asked about the recording and slides of this seminar. We will publish the recording tomorrow or the day after tomorrow. It will be on our YouTube channel and on our Bilibili account. And regarding the presentation, this question goes to Professor Gan, and eventually we can help you. We can forward you the presentation if that is not a problem for Professor Gan. Just you can always send me an email at this email address laura.baltis@icsi-BJ.ac.cn. So feel free, if you have any requests, to pitch me, to contact me, and I will make sure your request will be fulfilled.
The data after we do after the mission, we finish the test in the orbit, we will open the data immediately. So maybe 3 months after the launch. Yes.
Okay. Thank you very much.
Maybe Lola, you could also remind our audience that there will be a few talks on the Solar Orbiter mission in near future.
Yes, we will have, first of all, next in 2 weeks, we are going to have Professor Giovanna Tinetti's talk on the Ariel mission of the European Space Agency. It's going to be on January 27th, same time at 4 p.m. Beijing time, 9 a.m. In Europe. So feel free to join also this On Things to Come seminar in 2 weeks. And yes, we're going to start a series of seminars on the Solar Orbiter mission. The first one is going to be on February 24th with Professor Johannes Benkhoff. We will then have the following one with Professor Gabriele Cremonese on the 10th of March. And then Professor Murakami on the 24th of March, and finally Professor Saito on the 7th of April. Lots of dates. You can follow us on our social media channels to make sure you don't miss any of them, or you can always also send me an email if you're not in our newsletter. So you can also always follow our events. Thank you very much, Professor GAN, for your presentation. It was very successful. We received also positive feedback on Bilibili. Thank you very much.
Yeah,
and thank you very much for attending the webinar, and see you in a couple of weeks. Bye-bye.
Bye-bye.
Bye.